And the right-hand side. Now, let me refresh our memory on 1 over x. Very important. Like the square root of the function prime. So remember, we said that this is good to remember. 1 over 2 the square root of f times f prime. The same thing with 1 over x. 1 over x prime is good to remember if you can. It's 1 over x, negative 1 over x squared. So it's a good idea to have this committed to memory. So what will I have on the right-hand side? Yes, yes. Negative 1 over x squared times natural log of tangent x and plus 1 over x times 1 over tangent x times the derivative of tangent. That's, remember, tangent goes together with secant. So it's secant squared x. I think that this is not clear to everyone. Am I correct? It's not clear to everyone. Let's do this again, okay? Ready? Okay. So this is function 1. This is function 2, correct? This is natural log of a function. And we know that every time we differentiate natural log of a function, we get 1 over the function times the function prime. So that's why natural log y is 1 over y times the function prime, but I don't want to write y prime. This is the recommended notation for many reasons. Okay, now we are on the right-hand side. We differentiate 1 over x, and we get negative 1 over x squared. Remember the product rule? Should I repeat the power rule? I'm sorry, you know what I mean. So 1 prime times 2 plus 1 times 2 prime. Is that clear? Okay, so we differentiated this and we got that times the second function. Now plus. I copy the first function and I differentiate the second one. When I differentiate the second one, I differentiate log of a function. 1 over the function times the function prime. So 1 over the function is 1 over tangent times tangent prime, which is secant squared. Is that better? There is nothing we can do here, but we do have to multiply both sides by y. You can say yes, yeah, you can change 1 over tangent into cotangent. So you don't have a fraction, but it doesn't matter really. We are not going to do anything with it. So dy over dx equals, we multiply both sides by y. Is that clear why we multiply by y? Because we want to solve for dy over dx. So that's why we want to multiply both sides by y. But I copy y in the form of tangent x raised to 1 over x. So this is tangent x raised to 1 over x. And I copy everything else I have. Negative 1 over x squared times natural log of tangent x, and then plus secant squared x over x times tangent x. And that's the end of it. There's nothing else we can do here. And we should not. Any questions? Yes?
Would it be okay to write negative natural log of tangent x over x squared to combine those terms up from there? Right there. Could you write ln tangent x over x squared?
Oh, yeah. To change this into a fraction?
Yeah.
Oh, yes, of course.
Combine those terms.
Oh, yeah. It's a product, sure. So you can put minus in front. Yes, you can put minus in front and then x squared in the denominator. Of course. Yes. Any questions? Okay. Do you think we need other examples to look at? Yes, Tom. Yes, please.
There's just for fun, number 15 on 223.
Very good. Number 15. On the same thing, 223?
Yeah.
Very good. So I'm going to replace x by x because it's easier for everyone to see. So natural log of natural log x. Very good. Now, do not confuse this with the product. How do I know that this is not natural log times natural log x? Oh, I know, because natural log has to have an argument. And this one does not. This one has an argument. Is applied to x. This one doesn't. So it must be applied to natural log. Exactly. So it's not a prior, but it's a chain. Good. The chain rule inside a function composition. So then f prime of x will be, and you could literally do this till you get used to it. I'm differentiating the outer function of this. So what do I write? 1 over this, which is natural log of x, times this prime. And I will rearrange it. I will write 1 over x natural log x, because we don't like anything behind natural log. We don't like anything behind square roots. I would like to pick a problem between 27 and 30. You choose, or I will. We're asked to differentiate the function and also find the domain of the original function. They don't say anything about the domain of the derivative. They only want the domain of the function. Number 30? Okay, number 30. So f of x equals natural log of natural log of natural log x. This is a complicated situation. It's not a simple case. In order to find the domain of this function, I have to start from the innermost function. So I see an outer, a next outer if you want, and an innermost. So I have to make sure, you see the difference, when we differentiate we go from the outer to the inner, but when I have to find the domain, I have to find a domain from the inner to the outer, because the inner function is the function that I evaluate first. If you say plug in 15, where will I plug in 15? In here. And then this number will be plugged in the next, and then this number will be plugged in the next. So finding the domain goes inside out, differentiating outside in. Okay, so now I need to remember the graph of this function. And if you remember, we have several graphs that we committed to memory. The graph of natural log x is this. And we discussed it several times when we looked at limits. So this is very important. So what is the domain? Yes. So the domain of this, do not erase it like that, I'm just making a point. The domain of this is x greater than 0. Would you agree? Assuming I don't have anything else, I'm done. Correct? But now here comes the second step. The second step says natural log of natural log. So now this natural log must be greater than 0 for this to exist. One more time. For this function to exist, x must be positive. For this function to exist, everything here has to be positive. For this one to exist. So that's why natural log x must be positive. But look at the graph. And we know that this is 1. When is this function positive, strictly greater than 0? Only for x? Exactly. So now this, the domain of this function, is x greater than 1. So now I have the domain of all this. So that's restricted now. Well, what about the natural log? Can I apply natural log to any number greater than 1? I'm done. There is no other condition that I have to fulfill here. So I think we should do this one more time. So we had natural log of natural log of natural log x. Okay? So this is function 1, this is function 2, this is function 3. I start with function 3. Function 3 is natural log x. Well, x must be greater than 0. Function 2 is this. Natural log of whatever has to exist. Well, this whatever has to be greater than 0. But for this to be greater than 0, this has to be greater than 0. Because this is what I have in here. This is the function that I had. So for this to be greater than 0, it's clear that the domain must be between 1 and infinity. So that is clear now that this function exists for x greater than 1. Now I'm moving on to the first one. But since x is greater than 1, and all this number is always positive, then there is no restriction needed for the first one. Because all this will be guaranteed to be greater than 0. So there is no additional restriction that I need for the first log. When x is greater than 1, this is positive. And then natural log will exist. And for this to be greater than, for the inside to be greater than 0, then x must be greater than 1. So the domain of this function is 1 to infinity. Okay, now they also ask us to differentiate. Let's differentiate. So the function is f of x equals natural log of natural log of natural log x. So f prime. First, we differentiate the outermost function. So that must be 1 over whatever I have inside, which is natural log of natural log x. But now I have to differentiate what I have inside. 1 over natural log x, but now I have to differentiate what I have inside this, times 1 over x. Is this better? Any questions? I will rearrange and just write 1 over x, natural log x times natural log of natural log x. Very good pick. Did you get something else?
When I plug it in, it's x equals 2.7.
You plugged in,
ln of ln of ln x.
you're looking at the domain?
Yeah.
Let's take a look. Okay, so I want to change the viewing window. 0 to 10. And let's say negative. No, I didn't mean that. I'm sorry. Scale of 1 is good. That's fine. Y minimum. Let's say negative 5. Okay. To 10?
Yeah.
Or even
On mine, it's not showing it crossing the x-axis.
5. So
I use the trace function to follow it back, and before it doesn't exist, I get the lowest value of x to be 2.76 as the
okay, so I have a flaw in my thinking. Let's go back. Thank you for doing that. So this one to exist, I have to have greater than 0. For this function to exist, I have to have greater than 1. So natural log applied to greater than 1, because I have to look at where the function values go. Okay. So natural log, natural log, natural log x. Okay. So this function exists for x greater than 0. And natural log of this, natural log x, has to be greater than 0, which means x must be greater than 1. So now this natural log of natural log x to exist, this quantity, natural log of natural log x, must be greater than 0. So this to exist must be greater than 1. But for this to exist, this expression has to be greater than 0. Okay, so
I think it's trying to approach the point.
no, I just want to determine where it starts, because it has a vertical asymptote. So once we get the vertical asymptote, then we know the domain is from that vertical asymptote to your right. For this to be natural log, this is, okay, I have it here. So this is the natural log x. For natural log x of natural log x to be greater than 0, then x must be greater than 1.
So, at the,
And then, okay, so when y is 1, greater than 1, okay. So we have to set natural log of natural log x equal to 1. Natural log of natural log x equal to 1, which means natural log x must be e, which means x must be e squared. So e squared is roughly 7 point. So let me look at the graph one more time.
it's like 2 point something.
Natural log must be e. E. It's not e squared, actually. It's e raised to e when I solve this equation. E raised to e equals x. It's a very interesting problem. Thank you for picking that. So natural log of natural log of natural log x to exist, I have natural log of natural log x to be greater than 0. Let me see when it's 0. This is 0 when natural log x is 1, which is when x equals e. So I want this to be greater than e. So for this is your natural log of natural log to be greater than 0 means natural log x. So
When I plugged it into my calculator in the table, I put e, and then I put e plus a very, very, very little bit, and that ends up being
right,
very
that's
negative, so,
yes. So I think the vertical asymptote is e.
Right.
So for this to exist, I just want to check one more second. So this must be positive. I want to see where it's positive. It starts being positive when natural log x is 1. Where is natural log x 1 when x is e? So it has to be, the domain has to be e to infinity. I'm sorry. This is what I did. Sorry about that. So For this function to exist, this quantity has to be positive. So natural log x has to be positive. But first I need to know where it's 0. So I set the equation. I've created the equations equal to 0. So this is 0 when this is 1, because natural log 1 is 0. Where is natural log 1 0? And at e. It is at e. So it's 0. These are all increasing functions. So it's 0 at e. This is 0 at e. Therefore, this function will exist only for a domain between, or x values between e and infinity. So I do not know how to show you how to create the vertical asymptote here. So there must be a way in which we draw the vertical asymptote, or tell the software to draw it, because that would be the best thing to do. But the other way is just to plug in e.
Can't you just plug in for y?
Oh, I will get an error when I plug in e, because it has to be strictly the, say it again.
E plus 0,
Right.
0, 0, 0, 0.
Right. Anything but e. But if so this is, e is 2.71. So if I put 2.72, I will not get an error. If I put 2.73, of course, I will not get an error. And I can go back to 2.719, and I will not get an error. Thank you. I jumped into a conclusion over there too soon. My apologies. Very good. Thank you. Do we need more, or can we continue?
I still don't know how I would have found x equals e if I didn't use the calculator.
Okay, so let's discuss it again. So this is our function, correct? So this function exists if this quantity is strictly greater than 0. So I wrote this. So now my question is, where is this 0 first?
ln of e equals 1.
Yes, so first I solve the equation. So I can see where, because from that moment on, these are all increasing functions. So once I determine when it's 0, then I know moving up, it's to the right, in other words. From that point to the right, the function will be positive. So I had to create this equation. So my question now is, natural log of natural log is 0. What can I have here for this to be 0? It must be 1. There is no other number that I apply log to get 0. So then this piece has to be 1. So this piece is 1 only when x is e.
Right. Okay.
So from e to the right, I will have the domain.
I see.
But without determining the solution of the equation, I was not able to proceed. Because I have to, this is not possible, right? I cannot have equal to 0. That's why I cannot have equal to e, so that's why it's a parenthesis. But if I don't know where the function is 0, I will not be able to see where the threshold is. And the threshold is at x equals e. I should show a vertical asymptote from e to your right. But I had to find the 0 first of the function. Better?
Yep.
Okay. We don't want to choose one more, or we continue with applications now? Applications or another function? Okay, so we can come back. We'll have more examples. I'd like to apply what we have studied so far in different situations. So this is 3.7 applications. We looked at a lot of techniques. So the first 6 sections of this chapter dealt with technique of differentiation. Differentiation rules, product rule, quotient rule, chain rule, log functions, inverse trig functions, exponential functions, and on and on and on and on, right? So now let's see what we do with all this. So I'd like to start, the applications are easier than a lot of differentiation that we did today and in chapter 3 overall. Okay, let's look at problem 7 on page 234. The height in meters of a projectile shot vertically upward from a point 2 meters above ground level with an initial velocity of such and such. Finally, they're giving us the function h of t. So this is in meters, and that's 2 plus 24.5 t minus 4.9 t squared. And t is in seconds. T in seconds. Part A. Find the velocity after 2 seconds and after 4 seconds. Velocity at 2 and velocity at 4. I'm sorry.
Alright, so like, do we change it to x instead of t?
Yes, we can. However, this is specific t because it's time. But you can change it. Yes.
So if we had this question on test.
Yes, of course. Yes, I'm fine. But remember, if it's t, you have to write the measurement unit. Normally, if it's x, depending on the problem, right? But in general, when it's t, we really have to write the measurement unit. So don't forget to write the measurement unit. You can change the variables the way you like.
What is that?
T in seconds,
No, like the equation.
m in meters, so the h is in meters. V of 2, this is part A, 2 plus 24.5 t minus 4.9 t squared.
Acceleration of gravity.
Yes, it's exactly it. So how do I determine V of 2? What do I have to find first? I have to find V of t, which is h prime of t, very good, which is 24.5 minus minus
9.8.
very good. So we have the velocity function. We are asked to find the velocity after 2 seconds and 4 seconds respectively. All I have to do is find V of 2 and V of 4. I need my calculator. I really don't, well, I'm lazy. 9.8 multiplied by 2 and also multiplied by 4. And I got 4.9 and negative 14.7. So meters per second and negative 14.7 meters per second. It does not mean a negative velocity, but it means
It's going
the opposite direction. Indeed, that's all it means, opposite direction. Any questions on part A?
I found one of the first problems we had was doing the instantaneous velocity. It had 4.9, and because I keep seeing 9.8 meters, I've seen that forever, but I've never seen 4.9. Now I get the derivative of the derivative is the acceleration. So
Exactly.
that's why it's 9.8.
Exactly. That would be the next question.
Okay.
I hope. No, they don't. When does the projectile reach its maximum height? So B, when h of t is max. Let's look at the function for a moment. What type of function is it? Quadratic. Does it have a max or a min? It has a maximum because the leading coefficient is negative. But I don't want to use algebra, because I know you're going to plug in negative b over 2a and find the vertex, right? Well, I don't want to use the algebra here. So how do I know when the projectile reaches its maximum height?
When
The
derivative changes from positive to negative.
Exactly, when the velocity is 0, exactly. So when h prime of t is 0, in other words, when v of t is 0, same thing. And v of t is 0 means 24.5 minus 9.8t is 0. This is a linear equation, and I get t. and t is 24.5 divided by 9.8, and I got 2.5. 2.5 measurement unit, please.
Seconds.
Very good. So how long it takes the projectile to reach the maximum height? 2.5 seconds. In question C, what is the maximum height? What do I have to find? How do I determine the maximum height? I plug in the function, what? The time needed to reach its maximum height. So 2 plus 24.5 multiplied by 2.5 squared, and then minus 4.9 multiplied by 2.5 squared. Oh, I squared when I didn't have to. Let me change that. So 2 plus 2, yes, that's correct. Okay, that's correct. I got 32.625. Bless you.
Thank you.
Good. So the maximum height is 32.625 meters. When does it hit the ground? Part D. What do I have to do now to determine when does it hit the ground?
H equals 0.
Exactly.
T equals 0.
Age of t equals 0, when the height is 0. That's when the projectile hits the ground. So this is 2 plus 24.5 t minus 4.9 t squared equals 0. Quadratic formula, I agree, but not before we put it in descending order and eliminate the negative leading coefficient. So I'm multiplying everything by -1. I have 4.9 t squared minus 24.5 t minus 2 equals 0. And yes, the quadratic formula, of course. So t equals positive, because I multiplied both sides by -1. Because I don't want a negative number in the denominator. You don't have to do that. I just don't want a negative number in the denominator, because I may forget. 24.5 squares minus 4 times 8 times c. There are two negatives. I'm going to say 8 times 4.9 divided by 9.8. I know you know how to do this, but let me show you how I would put it in the graphing calculator and not do it step by step. Just put the whole thing. And when I put the whole thing, I will definitely put parentheses around the numerator. I will not need parentheses around the denominator because it's only one term, but if you want, you can. And I will definitely put parentheses under the square root. And I will do it in one step. Everything okay so far? Yes? Yes? Okay. So left parenthesis, I think we did that before, I see it there, but maybe with another class. So 24.5 plus the square root in parentheses 24.5 squared plus 8 times 4.9, close the parenthesis, under the square root, go outside, close another parenthesis, and divide the whole thing by 2. 9.8, I'm sorry. And then I repeat with second and entry. I don't want to type all this one more time. Second and entry. It copies everything you had. And for you, it's easier with the calculator, but for me, I have to go back step by step and overwrite. It's going to pass it, of course. Okay, come back. Minus. Very good. So I would completely disregard the second one because it's a negative time. But I had to calculate it. So t equals 5.08 seconds. You can say, but since it's the projectile already it's up in the air, so yeah, just to make sure. But you're right. If you had said, well, I really don't care about the other solution, I would have said correct. Last question here. With what velocity does it hit the ground? What is the velocity?
24.5 minus 9.8.
So yes,
H prime of 5.08.
exactly, or v of 5.08. So this was 24.5 minus 9.8 times 5.08. And the answer should be negative because when we shot it up in the air, it's going to go up. It's increasing the distance, and when it comes down, it's a negative velocity. So let's see, what did we get? 24.5 minus 9.8 times 5.08. I got negative 25.2. Correct me if I'm wrong. And this is meters per second. It's velocity. And don't get scared. It's not a negative velocity, but it's just a direction. Any questions? Any questions? I like to look at the cost function now. Last one, I promise. Okay? But this is much easier than all the technique that we looked at, isn't it? Would you agree, or you prefer the technique? I mean, differentiating functions and. Okay. It's longer to differentiate than answer. Yeah, I agree. I agree.
What kind of vegetable you want for dinner?
Depends on the time of the day too, right? Let's look at 31, page 236. Okay, the cost in dollars of producing X yards. So X is in yards. Cost in dollars. And here's the function. C of X equals 1200 plus 12x minus 0.1x squared and plus, I think I see 3 zeros, 0.0005x cubed. So you are the manager of this factory and you produce yards and you have a function. You determine it yourself. You have a function that gives the cost of producing X number of yards. Okay, first question. Find the marginal cost function. Marginal cost function is nothing else but the rate of change of cost at any point in time for any x, where the function is I'm looking for a specific word. Thank you, differentiable. But this is a polynomial function. Polynomial functions are continuous, no corners, no cusps. They are always differentiable everywhere. Okay, so then what could the marginal cost be then? What is the notation and how do I get it? Very good. So this is 12 minus 0.2x plus 0.0015x squared. This is the marginal cost. It gives the rate of change of cost with respect to X yards of fabric. Should be squared yards, but the formula is given for X and we cannot dispute that. So X is in yards, not in squared yards. Okay, part B. Find C prime of 200 and explain its meaning. So C prime of 200. Let's explain the meaning and then calculate it. What can this be?
The rate of change in cost of fabric in dollars per yard?
Yes, in dollars per yard, perfect. When the production level is
200 yards.
200 yards. So it's the rate of change. The rate of change of cost with respect to X, which is yards of fabric, the rate of change of cost with respect to yards of fabric at the production level of 200. So now 12 minus 0.2 times 200 plus 0.0015 times 200 squared. Do you need me to repeat the cost, what it represents? Okay. Good, so I'm finding this number. 12 minus 0.2 times 200 plus 0.0015 times 200 squared, and I got 32. And yes, 32 is in dollars per yard. Part C. They're asking us to compare C prime of 200 with the cost of manufacturing the 201st yard of fabric. Compare this to the cost of manufacturing the 201st yard of fabric. Okay. Nope. Let's discuss this. Let's suppose we own this factory and we manufacture 200. And we have a meeting and one of you says, what happens, what would the cost be if we don't manufacture 200, but we manufacture 201 starting from tomorrow? How will I determine that? I will plug in 201, correct? To find the cost for 201 every day. I don't know if it's per day or per month or whatever. Okay, so now the question is, let's see the difference. How much more it will cost us, that 201st item? That's how we know. From the cost for 201, we subtract the cost for 200, and the difference will give us exactly how much is that additional yard of fabric to produce. So don't think about this one just yet. So the cost of manufacturing the 201st item will be C of 201 minus C of 200. I would prefer putting this function in instead of plugging it in. It's up to you. What would you like to do? Tell me what you would like to do. You want to put this in y equals and determine C of 200 and C of 201? Okay, so if that's what we want to do, let's put in the graph and calculator in y equals. I'll have to clear what I had before. So I have 1200 minus 2x. No, how did I come up with that? Plus 12x. And then minus 0.1 x squared. And then plus 0.12315. No, it's 5. X cubed. Okay? So then I go to second and table. I plug in 200 and I plug in 201. Okay, so 201 minus 200, now I copy them. I get, let me see what that is exactly, and if it has more than, okay. So C of 201 is 3632.2005, and C of 200 is 3600. So I copied them. Yes? So here's what I got. And now I'm going to subtract. So what do I get? $32.2005 per unit or per yard. Same thing. Now they are asking us to compare, as the final step, they're asking us to compare this to this. So let's compare the two. And make a decision. Make a decision whether you're happy with this, because there is a minor error. This is exact. This is the exact cost, no questions. This is not the exact cost. This is close, and it will always be very close, but it's not the exact. So for the production of fabric and yards of fabric, I prefer this and not the exact, because it took me much longer to do this than to find the derivative and plug in one value in the derivative. And I know that this predicts, so maybe we should write this down. So this, C prime of 200 predicts the cost of the 201st item. Yard, you know what I mean by item. And this is the exact. So now my question is this. Since we're talking about yards of fabric and not about human lives and not about medicines that have to be put on the market, would you be willing to live with this versus this? So would you tell your boss, well, I can predict already for you the cost of the 201st item. You can check later, but it's going to be very close to 32. But I'm telling you now, it's going to be very close to 32. Because that's what C prime of 200 is. But now if we're talking about, you know, life and death situations, maybe this is huge. The 0.2 versus 0.0, this decimal part, that may be very important. So it depends. However, the lesson from here is that C prime of 200 will always predict the cost of the next item, which is 201st or 201st yard. And this is a lesson that we take from calculus. And at the end of this chapter, you will see that we are going to be able to, let's say, evaluate the cube root of 1002 without a calculator. We will be able to find tangent of 44 degrees without a calculator, which wouldn't be possible without calculus. So at the very end of this chapter, chapter 3, we're going to learn is based on this idea, what we just did. So we're not going to call it cost or marginal cost, but it's the same thing that we're going to apply. And we will be able to determine these without a calculator. Any questions for me? Is there anything that you would like to go back to? So here's where we are. Just one more second, then I'll let you go. We are still working in 3.7. So I'm hoping that you will, between now and Tuesday, you will finish everything from chapter 3, including 3.6 from the checklist, and come back with questions. So we do have 3.7 still to work on. We do not cover 3.8. It's part of pre-calc. And 3.9 requires possibly 2 sessions. It's a lot. 3.10, very simple. It is exactly what I was talking about, differentials. And 3.11, simple. I'm just going to show you 3 functions, basically 2, to tell you the truth. And that's it. So I'm estimating test 3, possibly 2 weeks from today. So today is the 4th, and if I add 14, so I'm thinking of 18. For test 2. For test 2 from chapter 3. And we'll decide together. So, which means the checklist has to be finished by a week from Tuesday. But it all depends on whether we, finish. We basically have 3 more sections to go. Basically about 2. But 3.9 is huge. The related rates. Thank you so much for staying. Have a good weekend. Call me if you have any questions, and I'll see you on Tuesday. Please stay if you want to work on anything or if you need any help.
So,
Yes.
I didn't hear my accounting teacher right today, I don't think, but I might have to miss the first hour of Tuesday again.
Is this coming Tuesday? Okay.
Maybe.
Well,
I
one
think
of
the
them.
exam is on Thursday, so.
Oh, next week?
Yeah.
Oh, so at least there is no conflict this time.
No.
Okay, good.
I think that's my only exam that day too, so that's good.
Okay.